Hello, everyone. Today we continue with bilinear and quadratic forms. That's what mostly the most recent homework is about. So we are going to talk about the same thing. Also, I wanted to say one more thing. Previously, if you remember, I I suggested a book to you, the Berkeley book of math problems. I told you it's kind of good book to look at. I want to tell you one other place you can look for good questions and find some interesting problems. That's actually Stack Exchange for Mathematics, the website. The interesting thing about this website, probably as you know, is that you can go and ask your math questions or answer to questions other people have asked. But there's another way you can also use this website, which I did, and I found it quite interesting. So usually when I want to learn about a new topic which I don't know much about, let's say I want to learn about bilinear forms. One thing I do is that usually after just reading the basic definition or the basic theorem, you can go to this website and search all questions related to this concept, for example, to bilinear forms. And then you would see all the questions people have asked about bilinear forms. The interesting thing is that you can read the questions, you can try to solve it yourself, and then you can read the answers other people have given. The reason I like this style of reading questions and trying to solve them, maybe more than just a problem book, is that the difference is that you would get more human interaction, which probably you wouldn't get from a book. Um, that's one point. I mean, on the other hand, the good point about a book is that when you read a book, there's a greater chance that that book is written more rigorously and there shouldn't be any mistake in it. Probably there are less mistakes in a book. If you read online on a website, there's a greater chance that there are mistakes and mathematical errors in it. But on the other hand, you really would get human interaction. You would see someone is asking a question, you would read the question, you would think about that, and then you read the answers other people have given. Sometimes the answers are wrong. Someone has written a comment saying, no, your answer is wrong because of this reason. And people are arguing. You can even read those. And sometimes, reading all these comments and different ways people are thinking and speaking about the problem, giving partial answers, suggesting that maybe if you look at this reference, you would understand more. This sometimes gives me a better feeling about the whole concept. So that's not a bad idea. And I've tried this technique to use a few different things, especially when I was younger, not so much anymore. But it really helped. You can try that. Sometimes you can't even kind of predict where you would end up. You would start with a question and then people say it's related to this other question and you read that and you go to another link and you continue and you would end up finding yourself in some area of mathematics which is quite interesting without kind of predicting that. Sometimes it's nice to get lost in these discussions. Anyway, you can take a look at that specifically for this course, linear algebra. It's there's a quite rich database of questions which you can take a look. Okay, let's start. Let's start with bilinear forms and quadratic forms and these things. So I would start from a question from the book I recommended to you. This is the question. So suppose, well, you're familiar with quadratic forms, right? Let's say we have a quadratic form. Let's consider the easiest case. Let's say we have a quadratic form like this. A quadratic form which sends a real number x to ax squared, where a is just a real number. right? Very simple. It's like a function from R to R. You can think about this as a function. Let's show it with Q. You can think about Q as a function from R to R, which sends x to ax squared. So as you know, we say a quadratic form Q is, for example, positive definite. If, well, let me ask you, what is the definition of being positive definite?
If q of x equals 0, if and only if x equals 0, and if q of x is greater than or equal to 0 for all x.
That is correct. So in other words, q of x is positive for non-zero x. If x is 0, of course, the value of qx would be 0. Right. So that would be positive definite. So for example, in our case, when is this specific given q is positive definite? It would be positive definite if ax squared is positive when x is non-zero. And that's, of course, true if and only if a is a positive real number, right? But let's make it slightly more complicated. Let's suppose Q is a quadratic form from R squared to R. It takes two real numbers, say X and Y, and the value is defined as AX squared plus 2BXY plus CY squared. This number 2 is just merely for convention. It doesn't really matter. So the question is, when is Q positive definite? What is the condition for Q for being positive definite? Q is positive definite if and only if something. Okay, if you have not seen this question before, think about it for maybe a minute, and then I will tell you what is the answer. So let's first understand, what does it mean for a Q of x and y to be positive definite, right? Because it doesn't take a number now, it takes two real numbers, or we can think about it as a function which is taking a vector in R2, right? So it's kind of similar. Q is positive definite if for any vector xy in R2 where this vector is non-zero, which it's not the vector 0 and 0, then we would have Q of x and y, the Q for this thing would be positive. That would be so for example, it should be positive even for a vector like 0 and 1 or 1 and 0. It can only be 0 when the vector itself is 0, which means both components are 0, right? Okay, does anyone have any answer to the previous question? So let's write it down again. Q of x and y was equal to ax squared plus 2bxy plus cy squared. That's our quadratic form. Do you have any guess? We don't need to give a final answer. Let's see. I want this thing to be always positive, right? When x and y are non-zero. What can I do?
I guess for one, you could observe that x squared and y squared are always positive or 0. That's given that xy, we're assuming xy 3 non-equal to 0, 0. At least one of them has got to be positive.
That is true. That's correct. Yeah. That's one answer, which is correct. One thing we can do, we can try different numbers, right? For example, if it's supposed to be positive for non-zero vectors in R2, I can try something like this. I can try to say Q of 1 and 0 should be positive, right? But what is that? That would be A times 1 squared, which is A, plus 2B times 1 times 0, which is just 0, plus C times 0 squared, which is again 0. So that would be A. And that we want that to be positive. So A has to be positive, right? What else I can see from this method? What else does it tell me? Look what other vectors I can try and what other information I can get about this quadratic form. So what other vector do you think I should try?
Maybe 0, 1.
Yeah, that's a good idea. Let's try 0, 1. I would get 0 plus 0 plus C, and I want that to be positive. So it tells me C is also positive, right? So what can I say about B? How can I bring B into the picture? Let's try maybe 1 and 1, huh? Let's see what we would get. It would tells us A plus 2B plus C should be positive. That's one other thing. And we can try a lot of different numbers, right? And we would get a lot of relations. But it's hard if we continue this method, it would be hard to be sure that we have, for example, a sufficient condition, right? All these things are necessary, but having a sufficient condition is more might be also important. So I see a comment, complete the square, about the last one.
About Q.
Or the quadratic form itself.
Yeah, the quadratic form.
Okay. How should I do that? Do you mean, well, there are different ways to do it. So let's see. We have x squared plus cy squared plus 2bxy. It is equal to, well, let's write it like this. Let's see. We know a is positive, so it's non-zero. I can write this as a times x squared plus c over y squared plus 2b over a xy. And that is equal to a times x plus square root of c over a y, the whole thing squared, minus 2 square root of c over a x y plus 2b over a x y. Right? That would be completing the square, which is equal to a times x plus square root of c over a y squared plus 2b over a minus 2 square root of c over a x y. Okay. What next? So we want this thing to be positive. We want this to be positive. And we also know A is positive. It means the remaining part should be positive. This should be positive. Okay, what does it tell me? Can I use it?
I don't think so, because you don't know the sign of X and Y.
That is correct. Sign of X and Y can be anything. Let me, that's, oh, you said, I mean, X plus B over A squared plus something squared. Let me think. Well, but that wouldn't give us this. I see. That's actually a good idea. I understand what you mean now. So let's say this is the first way we can complete the square. It seems let's see if there is another way to do it too. So I think the comment now says, can we do it like this? Can we write it as something squared plus something else squared? Is it possible to do that? Can we write down this quadratic form as 2 parentheses squared? Is it possible or not? Well, which I think one of them is supposed. So do you mean you want one of them only should be a function of X and the other one a function of Y? Is that what you're looking for?
No, I wrote it wrong. I meant, sorry, I meant A times X plus B over A times Y, and then all that squared. Just like in the second derivative test for functions of 2 variables. That's what, like, that's my motivation for it, is like when you're doing the second derivative test for 2
So
variables.
what would be the next parenthesis? What would be inside the first parentheses?
So in the first one is X plus B over A
X
Y,
plus B over A Y.
and then
Okay.
outside is an A, so that
Okay.
takes care of the first 2 terms, and then you have a second term that I haven't calculated yet.
Ah, I see. Let's take a look. Well, let's see. Let's see if it helps. Let's see if there is any way we can make this work. So if we do that, the first thing would be ax squared plus b squared y over a plus 2bxy. That's what we would get from the first thing. I don't think there would be. Okay, yeah.
And then the next term would be B squared over A plus C, all in parentheses, times Y squared. And so I guess I wrote it wrong. It's not something squared, it's something times Y squared.
Yeah, okay, would you repeat? So there is B outside? Is that what you're saying?
Yeah, I'm saying the only thing that's squared is Y, and then outside in parentheses we have B squared over A, or sorry, we have C minus B squared over A.
C minus B squared over A. This thing times Y squared. Is that it? Yeah.
Yeah.
Okay.
And then those are equal, I think.
Yeah, I think so. Yeah, that is correct. This is the remaining part. That is true. Okay, let's see. So we want this thing to be positive. And we already know this is positive. So if this part is positive, then everything's good. So if C minus B squared over A is positive, then Q is positive definite. And this says AC minus B squared is positive. Now, why is it? So this is necessary, right? This is This is necessary. Is it also sufficient? Sorry, let's see. Is it sufficient or necessary? It is actually sufficient, sorry, because, so let me rewrite it. So this is sufficient. Because if we have this thing positive, we know this thing is positive, therefore Q of X and Y would be positive. But conversely, does it have to be positive? So maybe this is not positive, maybe sometimes it's negative. So this thing is negative, but this other thing is positive and it's so large that it cancels the negative part and still the sum is positive. Is that possible? In other words, is it necessary for this term to be positive? Okay, yeah, great. So let's look at one example. Let's see, x equal to minus b and y equals a. Let's try that. Let's see what would happen. X equals to minus b and y is equal to a. If we have that, here we would have minus b plus, and here we would have b, and this would be 0. Here it would be a squared times this other thing. A squared is positive, so this multiplication would be positive if and only if this term here, AC minus B squared, is positive. So it's also necessary. So this condition is necessary and sufficient. So you are completely right. I would repeat your proof, which was very nice, in slightly different way. I would just rewrite that, okay? So when we have a quadratic form like this, a squared plus 2bxy plus cy squared, there is a slightly different way of writing this too. You can write this as this new way. So we have this vector x and y. Consider this matrix A. This coefficient of x squared would go there. Coefficient of xy should come here. Maybe I should say that 2bxy can be, you can think about it as bxy plus byx, okay? So so let's say this is the place for xx. This is the place for xy, which is b. This is the place for yx, which is b. This is the place for yy, which is c. I complete this matrix in that form. Suppose I'm just constructing a matrix like that, and then multiply it by xy. So if we do this multiplication, let's try to see what is the result of this multiplication. So we would get the multiplication of the first two. We would get ax plus by, and then bx plus cy. And then we should multiply that by x and y. Okay, sorry, I wrote it wrong. It would be like this: ax plus by and bx plus cy. Okay, and then the result of the second multiplication would be ax plus by times x plus bx plus cy times y. And the result would be ax squared plus byx plus bxy plus cy squared, which is equal to what we started with. So if I just want to summarize what I said, this quadratic form can be written as xy times this matrix A, B, B, C, X. So you know there is a way of going from quadratic forms to bilinear forms, and from bilinear forms to quadratic forms. This thing here is a quadratic form. Now, when you have a bilinear form, if you have a fixed basis, this bilinear form would have a matrix. This matrix here is actually the matrix of the bilinear form in a basis. Okay. So I want this to be positive for any vector x and y. Let's show this vector x and y with v. So it just says v times this. Let's show this matrix with q. We want v transpose qv to be positive. That's what we want. For any vector v which is non-zero vector in R2, right? Now, this is pretty much related to the topic we started during the previous week, if you remember. Look at Q. What is the important property of Q? Look at this matrix Q. What do you see?
It's symmetric.
It is symmetric. So Q is symmetric, right? BB, right? It is symmetric. What did we learn about symmetric matrices? We proved the whole time during the previous week, we studied symmetric matrices. What did we learn about a symmetric matrix? You can just unmute yourself and say it. That is correct. Its transpose is equal to itself. That's the definition. But there is a good basis for them. We know something about symmetric matrices. Think about that for a few seconds.
Diagonalizable.
It means there exists another matrix P such that it is invertible, and P inverse n by n, here it would be 2 by 2, P inverse QP is diagonal, right? Therefore, this matrix we have here, A, B, B, C, is diagonalizable, right? So let's define this diagonal matrix, P inverse QP by D. And what are the elements on the diagonal? Do we remember? What were those elements on the diagonal?
The eigenvalues.
The eigenvalues. And we learned something about these eigenvalues of a symmetric matrix too. What is the property of the eigenvalues of a symmetric matrix? They are real, right? That's what it means basically when we say it is diagonalizable. We mean over R. Okay. Now, remember, we want it to be positive definite, and we saw being positive definite means xy times this matrix Q times xy should be positive. But if I call this xy this vector v, it means v trans, well, it is v transpose, and this one is v. V transpose QV should be positive, right? Now it's interesting. Look at this matrix P. It's an invertible matrix, right? So if I multiply, let's see. Yes, so if I multiply this this vector v by p, I would get another vector. Let's call that u. The point is that if V is non-zero, if V is non-zero, therefore U would be non-zero too, because P is invertible. So its kernel is only 0. Okay. In that case, well, let's call U to be P inverse of V. Doesn't matter, because if P is invertible, P inverse is also invertible. In that case, V would be equal to P U. I can just plug in that inside this equation we have. So we have V. Instead of V, I would write PU transpose Q. And then I have V. Instead of V, I would write PU. This matrix should be positive, right? Okay. What does it tell me? So if you remember, we proved one more thing during the previous meeting. We proved we can also assume something about the matrix P. We showed the matrix P, which appears here in diagonalization of Q, we can assume it is an orthogonal matrix. What does that mean? That means P inverse is equal to P transpose. Okay, that's what it means. Now, why is it important? So here we have V transpose Q V, and if we just define U to be P inverse V, we would get P U transpose Q V, and it would be equal to U transpose P. Sorry, here I would also have PU. P transpose Q PU. So if P transpose is equal to P inverse, this thing is our diagonal matrix in the middle. So this is equal to U transpose lambda 1, lambda 2, U. And this should be positive. This should be positive. Now this is very good. Why? So this vector U, let's write it as, I don't know, let's say U1, U2. So U transpose would be U1, U2, and then multiplied by this diagonal matrix, lambda 1, lambda 2, times U1, U2. This should be positive. But if we do the computation, we would say it is equal to U1, lambda 1, U2, lambda 2, and then we should multiply that by U1, U2, which is equal to U1 squared, lambda 1, plus U2 squared, lambda 2. So this should always be positive. For any non-zero U1 and U2. What does it tell us? When is it? What is this? What does it tell us? This thing should always be positive for any non-zero U1 and U2. So for example, if I take U1 to be 1 and 0, it means lambda 1 should be positive. If I take U1 and U2 to be 0 and 1, it shows me lambda 2 should be positive. So it simply tells me the eigenvalues should be positive. So if I want to summarize, when you have a quadratic form, you can construct this matrix out of it. It would be positive definite if and only if all the eigenvalues are positive. Okay. Is it clear? Is there any question here? Okay, so the eigenvalues should be positive. Do you remember what is the sum of the eigenvalues and what is the multiplication of the eigenvalues? Does anyone remember? What is the sum of the eigenvalues? Yes, it is trace, which here, trace of Q would be A plus C. and their multiplication would be AC minus B squared. So these should be positive.
Yes, and that's and the product of eigenvalues is the determinant.
Yeah, that is true. This is the determinant of Q. And we got this. We got this equation. And we saw that A and C we got the equation that A and C should be positive. So their sum, of course, should be also positive. Now, the interesting thing is that this is correct. We didn't use, actually, in our proof, in our second proof, we really didn't use that. It should be a 2 by 2 matrix. It really works for any n by n matrix and for any quadratic form. So in general, when we have a quadratic form Q, say of x1 up to xn, we can, in a similar way, we can construct this matrix Q, and then we want these eigenvalues to be positive. So for example, if we had Q of x, y, z, if it was, say, let's go one step further. If it was equal to ax squared plus 2bxy plus cz squared plus let's see, what is the next variable used here? Okay, plus 2dxz. Sorry, this was y. Plus 2dxz plus 2eyz plus fz squared. So we should have all multiplication of x, y, and z 2 by 2 multiplications. So if I want this to be positive definite, again, I should form this matrix x, y, z, x, y, z. So what is the multiplication of x and x? What is x? It is a. What is x, y? Again, as I said, think about 2bxy as bxy plus byx. So here in this place for x, y, I would write b. In this place for x, z, I would write d, because this 2dxz is x dxz plus dzx, right? And then yx would be b, yy would be c, yz is e, zx is d, zy is e, and zz is f. And I need the eigenvalues of this matrix to be positive. And there's a funny way of saying that these matrices should positive eigenvalues. If the eigenvalues are positive, the determinant should be positive. So it means the determinant should be positive. There's a way of saying all the eigenvalues here are positive. It would be actually equivalent to saying the determinant of this matrix is positive. The determinant of this submatrix is also positive. And determinant of this submatrix, which is just the number a, should be also positive. And this, in a trivial way, you can think what would happen for 4 by 4 matrices, 5 by 5 matrices, etc. You would get a sequence of submatrices getting smaller, and you just want the determinant of all of them should be positive. Well, this is actually equivalent to saying all eigenvalues are positive. Okay, is there any question here?
What are you using as the definition of the quadratic form to make these setups?
Yeah, so the definition here we came up here is this formal form. This you can think about it as the generalization of what is written here. For any numbers of elements, x1 up to xn, say x1 up to xn, we would have q of x1 up to xn, and it would be something like that, xi, xj, say when I is less or equal than j, and then multiplied by bij. So it takes a vector, multiplies them with some coefficient, and take the sum. That's the definition we set up here. Another way of thinking about it is something comes from a bilinear form. Suppose we have a bilinear form B from a vector space V to its field F. So it would be a map B bilinear from V times V to F. You can assign a quadratic form to that. So quadratic form Q of anything like X can be defined in terms of this bilinear form. Can you guess that? Yeah, it would be just B of X and X. So the other way of thinking about a quadratic form is that it comes from a bilinear form. It would be, and that would always be the case. So that's the way of going from bilinear form to quadratic form, and that's always the case. You can also go from a quadratic form to a bilinear form. So suppose we have a quadratic form Q from V to F, we can construct a bilinear form from that. B from V times V to F. I should define what is B of now X and Y. What would be the definition of bilinear form if we have Q? If we know what is Q, how can we define B? Does anyone know what is the answer here?
B of xy equals q of x plus y minus x q of xx minus q of yy all over 2.
Well, you don't need to say Q of X because Q just
sorry.
takes one thing. Yeah, that is correct. So in other words, another answer to your question is that quadratic forms are really just one-to-one correspondence with bilinear forms, and we know what are bilinear forms. Okay, great. That's great. So let's look at an example just to give an answer to your question too. Suppose I have Q of X and Y, so just something. Let's say X squared plus 3xy plus 2y squared. Okay, I'm saying this gives you a bilinear form B from, can you guess from where to where? Let me wait so you would guess. What would be the domain of B?
R squared, I suppose.
R squared?
Right, Q of xy.
R squared, well, I mean bilinear.
R squared cross R squared.
Cross R squared, 2R. So I'm saying this quadratic form, or any given quadratic form, gives you a bilinear map. How should I define that? So what is that map? You know, a bilinear map can be given by a matrix, right? How does it work? So, you know, we have E1 and E2, the basis of R2. So the matrix I would assign to this bilinear form in this given matrix would be B of E1, E1 here, B of E1, E2 here, B of E2, E1 here, and B of E2, E2 here. Okay. Now, so to any bilinear form can be presented by a matrix. Now, on the other hand, I'm saying you can construct that matrix when you have a quadratic form. What is the matrix I would assign to that bilinear form coming from this quadratic form? I would simply write down the coefficient of x squared here, which is 1, coefficient of xy here, which is 3 over 2, coefficient of yx here, 3 over 2, and coefficient of y squared here, 2. That gives me a matrix. I interpret that matrix as matrix of a bilinear form. If I do that, it means, well, it means B of E1, E1 is equal to 1. B of E1, E2 is equal to 3 over 2. B of E2, E2 is equal to 2. Right? Now, that kind of gives me the bilinear form explicitly. So let's go to the next page. So as I said, for example, we started with some quadratic form, q of xy, which is equal to x squared plus 3xy plus y squared. And we noticed it gives us some b, where b of e1, e1 equals to 1, b of e1, e2 equals to 3 over 2, and b of e2, e2 is equal also to, was it 1 or 2? It's 2 here. Now for any x and y, for any x and for any vectors, let's say v1 and v2, the vector the vector v1 itself can be written as x1, y1, and the vector v2 can be written as x2, y2, right? So this is equal to, well, x1 and y1 is equal to x1, e1 plus y1, e2. And x2, y2 is equal to x2, e1 plus y2, e2, right? Now, because this is bilinear, I can expand this bilinearly, right? Do you agree? So if I do that, I would get, what would I get? I would get x, well, let me write that again so you wouldn't confuse. Okay, so if I expand this bilinearly, it would be b of x1, e1, x2, e1 plus b of x1, e1, y2, e2 plus b of y1, e1, x2, e1 plus b of y1, e2, y2, e2. Right, because it is bilinear. And it would be equal to x1, x2, b of e1, e1 plus x1, y2, b of e1, e2 plus y1, x2, b of e2, e1 plus y1, y2, b of e2, e2. Now, b of e1, e1 was 1, e1, e2 was 3 over 2. This was also 3 over 2, and this was equal to 2. So we would get x1, x2 plus x1, y2 plus y1, x2 plus 3 over 2. 2 y1, y2. So this would be the explicit bilinear form given by that quadratic matrix and quadratic form, and its matrix is exactly this thing given here. So we have, that's the point. So we have a way to go from quadratic forms to bilinear forms, and from bilinear forms to quadratic forms. And note that this, although we used matrix, but this doesn't depend on the chosen basis. The way it is really defined is that we define q of xy to be the way we defined the quadratic form, for example, here, or bilinear form using quadratic form, or conversely, when we want to define q for any x, we defined it to be b of x and x. These definitions don't use any specific matrix, although when we want to show it by a matrix, we fix a basis, but the definitions themselves don't use a matrix. So this way of going from quadratic forms to bilinear forms and Going back is kind of, well, what it is usually called a natural correspondence. You don't even need to fix a basis. Okay. Any other question? Okay, if no, we can stop our meeting here.